Hi, we are team number 30. Humans are driven by curiosity. This inherent tendency of exploring has led us through over 6 million years of evolution to today. Ironically, we also encourage our algorithms to do the same: explore, make mistakes, and learn from them. Despite the obvious similarities, many people still don't trust AI. Why? Because humans are scared of the unknown. The problem with many state of the art DL networks is that they are essentially black box in nature. Even the DL practitioners cannot explain with 100% confidence the predictions made by the networks they built themselves. To overcome this problem, specifically in the domain of speech recognition, our team decided to build interpretable neural networks to discriminate between small vocabularies of confusable phonemes under the guidance of Professor James Baker. We have also incorporated elements of human guided AI into our architecture. More about this later.
Now, coming to the task. When we took up this project, Professor Baker warned us that no recent research has been done on this task. To circumvent this lack of directly comparable results and relevant data, we built an end-to-end deep learning pipeline. We created a custom dataset for our experiments. Each one of us recorded over 38 isolated phonemes. We processed this raw speech data using a window length of 10 milliseconds and 40 log amplitude features sampled on a MEL scale. This process made us appreciate the effort that goes into creating a dataset. For example, a lot of thought went into how to generate the ground truth labels for each frame. Doing this manually was out of question. We finally bootstrapped the labels using the open source Google Voice Activity Detector.
While building our model, we struggled with striking a balance between performance and interpretability. We tried different approaches, such as autoencoders, to generate embeddings for speech data. However, we finally decided to move forward with an intuitive architecture, keeping in mind our goal of interpretability. Thus, we designed an ensemble of specialized neural subnetworks. Each of these networks was trained to be a high-performance discriminator on tasks informed by our prior speech knowledge, thus making our system an instance of human-guided AI. The tasks are divided into three categories: distinguishing between individual phonemes, pairs of confusable phonemes, and other specific tasks. Detectors which are trained to identify the presence of an individual phoneme are called phoneme detectors. To make each of these networks robust, a mixture of different phonemes and silence frames are fed during training. Each specialized classifier performs a specific task. It either discriminates between pairs of phonemes that confuse even native English speakers, or it differentiates between vowels and consonants, high and low vowels, etc. These networks are generalizable, making it easy to add new tasks. All of these subnetworks are combined together to form the initial layer of our complete frame-to-phoneme classifier network. We pass the input frame parallelly through all the subnetworks, concatenating their outputs and passing them to our final linear layer to get a distribution of probabilities across all the phonemes. We tried different modifications to improve our model. For example, we tried to incorporate context and introduce an RNN style of architecture. However, our performance actually declined. On analyzing, we figured out that this had happened because of a lack of temporal dependence in our dataset. We had processed the data such that there was no natural transition between different frames. Thus, context confused our model more.
To evaluate our classifier network, we used metrics such as precision, recall, and F-score. We obtained good results for most phonemes, as phonemes are the building blocks of speech and hence differ fundamentally. Having said that, there were certain special cases. For example, the discrimination between b and p spoken in isolation is difficult. In connected speech, these phonemes are mainly distinguished by their effect on adjacent vowels. Since our work primarily focused on isolated confusable phonemes, these phonemes achieved relatively lower precision and recall scores. To demonstrate the interpretability of our system, we plotted the contribution of each subnetwork to the final predictions by using weights of the fired neurons. The cool part here is that we were able to clearly identify where our model failed or did better. In conclusion, this system can be used in isolation as a frame-level phoneme recognizer or can be plugged in as the front end to a deeper backend system capable of performing specialized tasks like word detection by backpropagating the error all the way to the front end. The interpretability of this system is a small step in the direction of making DL networks more transparent. Debugging of input edge cases, removal of bias, and feature engineering would become more efficient as we would be able to see how different features affect the output clearly. Finally, from a real world standpoint, these networks can also be extended to domains such as assistive technologies, mobility, and healthcare. Thank you.